Enceladus is a small, quiet moon, quite unlike the mythological creature from which it gets its name. In ancient Greco-Roman mythology, Uranus, the god of the sky, was castrated by his son, Cronus, and his blood impregnated Gaia, mother goddess of the earth, and from this she had a child. That child was the giant Enceladus, who would fight against the gods of Olympus during a cosmic war for control over the entire universe. The story of Enceladus the moon is much less dramatic, but no less interesting. The sixth largest moon of Saturn, Enceladus is plain and unassuming at first, but upon closer inspection, it reveals itself to be an exotic and alien world. The surface of the moon is pretty much entirely covered in ice, which makes it extremely reflective. Because it absorbs so little light energy, the surface temperatures tend to be cooler than those of other Saturnian moons. The most reflective areas of Enceladus are its smooth ice plains, which are vast ice sheets unadulterated by impact craters. This directly suggests that the smooth plains are geologically young, having been formed relatively recently. Other regions on Enceladus are rugged, mountainous, and defiled by fields of overlapping craters embedded in the ice. Many of these craters give clues to their age by the degree to which they've deformed through the viscous relaxation of the ice. These rippling cracks and newly formed ice sheets strongly suggest that the surface of Enceladus is an icy shell surrounding a liquid water subsurface ocean, much like the Jovian moon Europa and the other Saturnian moon, Titan. The southern polar region of Enceladus is a particularly exciting place. It has hardly any craters, which suggests that the region is geologically young. It's rugged, with ridges and ravines and fractures, and when viewed from orbit, you can see that all these terrain features have formed around a series of 4 huge cracks, spaced about 35 kilometers apart from one another. Each one of these huge cracks is close to 130 kilometers long, about 2 kilometers wide, and 500 kilometers deep. These massive cracks on the South Pole are easily the most interesting part of Enceladus, because they're like nothing else on the moon, and they're the best place to look for life. From a general perspective, the entire moon is covered in fine-grained water ice, but the southern polar cracks are covered in larger, coarse-grained ice. As coarse-grained ice is exposed to the Saturnian magnetic field, it loses its crystal structure over a few centuries, and eventually crumbles into fine-grained ice. What this means is that the ice coming out of the cracks must be young. There's some geological process that's causing upwelling, where liquid water held under the surface is being pushed up and getting sprayed out through these big cracks. This upwelling produces massive geysers that blast out of the moon's south pole, feeding ice and dust into the E-ring of Saturn. This expelled ice dust from Enceladus is what composes the E-ring, so the moon orbits right through the heart of it, sending ripples in its wake through this ice field. Because of its proximity to Saturn, Enceladus is subject to heavy tidal forces. It also experiences tidal forces when it passes by the moon Dione. These tidal forces are strong enough to impart significant heat into the moon, which could theoretically allow it to sustain magma pockets in the upper core, which could then sustain geological activity, like chemical cycling in the icy crust. Although I should mention that we still don't know with 100% certainty where all of Enceladus's heat is coming from. Radioactive decay and tidal heating accounts for a lot of it, but not all. Where the rest of this heat is coming from is still a mystery. Enceladus is calculated to have a proportionately large but porous core, which is warmed as tidal forces cause it to warp and flex. The heat that's generated through this tidal activity would then melt the proximal ice, which happens to be the lowest layers of the icy crust, the ones that are lying right on top of the core itself. When this ice melts into liquid water, the water gets heated by friction as it runs through the pores in the upper core, and the water is also held under high pressure as the ice sheets above are pushing down on it. Any cracks in the ice would then be filled with this high-pressure liquid water. Now this is where it gets really cool. As Enceladus orbits Saturn, its orbit will regularly take it closer and farther away from the gas giant. When the moon is at the point in its orbit where it's closest to Saturn, the tidal and geophysical forces acting on it are compressing the surface ice. They're compressing the southern polar cracks, and so hardly any water can get out. The geysers at this point in the orbit are smaller, and they burst less frequently. Now when the moon is far away from Saturn, when it's at apoapsis in its orbit around the gas giant, the tidal and the geophysical forces at work aren't compressing the ice sheets. They're actually putting them under tension, and the massive southern cracks are pulled apart. As the cracks are widened by the tidal stress, they open up, and the liquid water inside is exposed to the vacuum of space. This extreme pressure differential causes the water to blast outwards, hundreds of meters above the surface and out into space. This is where stuff starts to get really interesting. The southern polar region doesn't just have this geological process that's found nowhere else on the moon, it's also anomalously warm. It's twice as warm as what was expected. This relatively high ambient heat signature makes the environment a little more tolerable for biochemistry, and as a result, this is also the only place on Enceladus where we've detected signatures of biomolecules. The Cassini probe detected simple organic molecules in the southern polar ice, concentrated heavily around the cracks themselves, almost as if they were leaking out from the subsurface body of water. These organics could, theoretically, be the byproducts of biochemistry, like some kind of living metabolism, but they've most likely been generated through purely physical and geological processes. For example, it's quite likely that methane is produced through a reaction between water and the mineral olivine. This methane is wrapped in water molecules to form a clathrate, and when the water gets blasted out of the geyser, the clathrates decompose, and the trapped compounds, in this case the trapped methane, gets released. Methane is one such simple organic molecule found in the geyser clouds, but the Cassini probe also detected simple organic molecules like ammonia, propane, acetylene, and formaldehyde. Now if you thought that this was exciting, there's more. It gets even better. Cassini sampled some of this water that's being blasted out from the southern polar geysers, and here it found something shocking. Complex biological macromolecules. These have a lot of atoms, 15 carbon atoms at least, and they're heavy, at least 200 atomic mass units and higher, which is much heavier than simple building blocks like carbon dioxide and methane. It's very unlikely that these macromolecules formed through the blind, unregulated abiotic processes of primitive organic chemistry. To make large polymers and other complex biomolecules that don't rapidly degrade and fall apart, you generally need a biological system that can generate and maintain them. Alternatively, these large macromolecules could be the products of organic matter that's decaying and breaking apart. In this case, what Cassini found would be the rotting remains of some alien organisms living in the subsurface ocean on Enceladus. Now, so far in this episode, you might be thinking that the subsurface ocean on Enceladus appears to be localized to the South Pole. It seems that everywhere else on Enceladus is barren, cold, and dead, but only here at the South Pole, along these massive fault lines in the ice, do we see the cool stuff, like heat and liquid water and organic molecules. But the reality is that the South Pole is just where we see those big geysers. The icy crust of Enceladus itself is actually completely detached from the rocky core, so the subsurface ocean is global. It spans the entire moon. This global ocean is estimated to be 26 to 31 kilometers deep, which is more than 8 times as deep as the oceans on Earth. Now, while all of this is very good news for life, there's a few details that we have to take into consideration. First, a big ocean might sound like a good thing, but it could also be not a good thing. A big ocean will need a stronger temperature gradient to maintain strong currents. Also, just like the open ocean on Earth, the open ocean of Enceladus would be relatively nutrient poor. When you're out there in the heart of the water, far from any shoreline and far from the ocean floor, there's a low concentration of minerals and nutrients and particles of detritus, so it's difficult for large complex life to sustain itself out there. Life will tend to concentrate along the shores, along the ocean floor, and along deep sea vents where nutrients and detritus would presumably exist in high concentration. However, Enceladus appears to have very salty water, which means that the more open regions will still be saturated with particles, like silicates and sodium and chloride salts. This likely bumps the water pH up to 11 or 12, which is extremely basic, and would be a problem for any potential life. Although that's kind of an Earth-centric assumption. Any life that emerged on Enceladus would inherently be well-suited and comfortable in its home environment, just like life here on Earth is well-suited and comfortable to our temperate, liquid water-bearing environment. The high pH and the saltiness of the water are believed to be the result of serpentinization processes on the ocean floor. Low silica mafic and ultramafic rocks get oxidized by water, and this releases two protons, which will bind together to form a molecule of molecular hydrogen, or H2. This process generates minerals like serpentine and magnetite, as well as a lot of hydrogen and a lot of heat, where the rock itself can actually see a temperature increase of more than 250 degrees Celsius. This heat, produced through the metamorphic serpentinization process, will warm the ambient water, and it will melt ice and make the environment that much more tolerable for potential biochemistry. The hydrogen that gets produced can be consumed and metabolized by chemotrophic microbes for energy. In 2017, NASA announced that they had found evidence strongly suggestive of deep-sea hydrothermal vents in the floor of Enceladus that pump out hydrogen produced by all of these abiotic geophysical processes. The presence of these hydrogen-spewing deep-sea hydrothermal vents is really exciting because methanogenic microbes can take that hydrogen and combine it with carbon dioxide to produce methane. This process of metabolic methanogenesis is how numerous microbes on Earth survive, and it's believed that some of the first life forms that ever appeared on Earth, some of the first organisms in the tree of life, were methanogens. So taking all of this data into consideration, it seems that Enceladus is ripe for life. It has a huge potential to be a life-bearing world. It has a globe-spanning liquid water ocean, with globe-spanning currents and a thick concentration of salts and tholins. This subsurface ocean exists because of an anomalous amount of heat trapped inside the moon, with the bulk of it coming from the core as its minerals interact with water, and as it gets flexed and warped by the gravitational influence of Saturn and the nearby moon Dione. Enceladus also has the chemical resources necessary to sustain a living ecology, including an energy source in the form of molecular hydrogen, ionic atoms in the form of sodium and chloride salts, nitrogen in the form of ammonia, and carbon in the form of CO2, methane, and numerous other tholins. Enceladus is much like Europa, in that both moons are covered in an icy crust with a subsurface ocean. Both moons are warmer than expected, thanks in part to the tidal forces of their parent planets. And both moons are host to organic chemistry. But the big mystery that remains unsolved is whether or not this organic chemistry has given rise to life. I certainly think it's possible. In fact, I'd go so far as to predict that right now, there is indeed a living ecology of alien microbes on one or both of these moons. Both Europa and Enceladus could already be on their way, with a young lineage of evolving microbes struggling to perpetuate themselves in the salty, frigid, pitch-black oceans. Now, if the biochemistry of life is way more fertile than we assume, or if there's some strange variables that we haven't discovered yet that greatly improves the conditions for life, then we might be sharing our solar system with advanced ecologies of complex organisms, like aquatic chemotrophic vegetation that feeds herbivorous alien fish, which themselves are prey to larger carnivorous alien fish. But who's to say that the alien life here would be some kind of fish analog in the first place? Maybe there's crustacean or worm analogs, or some kind of gastropod-type monstrosities. Maybe there's some kind of aquatic fungus that carpets the seafloor. Perhaps Enceladus has its own version of coral reefs, or deep-sea valleys and rifts warmed by hydrothermal vents, and these would be hotspots of biodiversity. Maybe there's even bioluminescent organisms that provide points of light in an otherwise pitch-black ocean. Or maybe they never evolved eyes at all, and instead use exotic electrosensors or mechanoreceptors that detect the vibration of prey animals swimming nearby. Now, obviously, I'm really deep in hypothetical territory here, but really, who knows what we'll find if we can get a submersible probe under the ice to explore these alien oceans. Enceladus is a hugely exciting area of interest for space agencies all across the world, because the moon is quite literally bursting with the potential for life.